Okay, welcome to the next video in our structure and function of the cardiovascular system. We're continuing to roll on with our description of the compartments, and I want to talk to you a little bit about the arterioles here in this video. So as you guys will recall, not much resistance to flow in your arteries, your large arteries, because the drop in pressure here isn't very high. Okay, so you know that you're driving a flow of 5 liters per minute. It doesn't take much pressure difference to do that, so the resistance must be low. But you'll notice that this pressure drop is really big in the arterioles, so that tells you that the resistance to flow relatively high. Okay? So, and we know that this is due to a change in the radius of the arterioles. Lower radius gives you a big increase in resistance. A small change in radius, a small decrease in radius will give you a big increase in resistance, and a relatively small dilation will give you a big drop in resistance. What are the things that alter the radius? You see some of them here. We can split them into two broad categories: local and central. The first thing that I want you to carry away, if you carry away nothing else, this dominates generally over this, okay? Local determinants of flow, local determinants of arteriolar radius dominate over central determinants of radius. That is, signals that come from your brain, which we're really talking about the sympathetic nervous system when we talk about that. And I'll briefly address that here. We'll address it in an entire lesson later on, okay? So local dominates over central, okay? And that's because, generally speaking, the local metabolic changes are an indication of tissue demand. In other words, usually these are local metabolites of metabolism, and when those metabolites go up, that means metabolism has gone up, and that tells your cardiovascular system, hey, this capillary bed needs more blood, okay? And so when it needs more blood, generally speaking, it gets it because the arterioles will dilate in response to an increase in these metabolites. And generally speaking, normally your body wants those tissues to get more blood. If they need it, they should get it, okay? This is more involved in maintaining mean arterial pressure as detected by the baroreceptors. We'll talk about that in a minute, okay? So your local factors in turn include the myogenic response to stretch. I'll tell you right now, not a whole lot known about that, but I will describe it. Heat and cold is a local response which will cause you to constrict or dilate. And histamine release will cause different changes in arteriolar diameter locally. Extrinsically, you have, of course, the sympathetic nervous system. You also have other peptides and various hormones that cause vasoconstriction, like vasopressin, angiotensin. We'll be talking about these later in the block. Epinephrine is really part of the sympathetic nervous system. It comes from the adrenal glands. Okay, so those are just some less important factors, local and extrinsic. Extrinsic meaning coming from elsewhere, not from outside the tissue. I'm not going to talk about I'm not going to emphasize these for the most part in this video. I do want you to know the local metabolic factors, the sympathetic response, and we'll talk a little bit about the myogenic response in a second. Okay, so the first thing I want you to remember, the resistance can be calculated through what's called Poiseuille's law. L is length. The longer the vessel, the bigger the resistance. This eta is the viscosity. The more viscous the fluid, the more the molecules stick together, the more they resist flow. So the more the viscosity, the higher the resistance. But by far, the most important thing to remember, if you're going to remember anything, remember this. It's exquisitely regulated by the radius of the vessel. Small changes in radius make for big changes in resistance. A small increase in radius will cause a large drop in resistance. This is in the denominator. And a small change in radius will cause a big increase in resistance. Radius, physiologically, regulates resistance to flow. Okay? Got it. All right. So this is a phenomenon known as autoregulation of flow. It happens to some extent in most arteries, but by far it happens the most in the kidney, and that's this is the response that you see in the kidney, and I'm going to briefly introduce it to you here because the myogenic mechanism is largely responsible for it. So you'll notice that flow through any vessel will obey Ohm's law. So here I have blood pressure, and as the blood pressure goes up, the change in pressure goes up. That is higher arterial pressure. That means higher pressure relative to the venous pressure. Flow will go up because the pressure went up. Okay? So this is an increase in delta P. This is an increase in flow that you see. Okay? Now, you hit a certain pressure, especially in the kidneys, about, about 90, something like that, 80 maybe. Okay? And then all of a sudden, the pressure can go up, but all of a sudden, the flow's not changing anymore. It's held constant. Okay? Well, delta P is continuing to go up over this range, but the flow is the same, so you know something must be happening to resistance, and that is true. What's happening is as delta P is going up, resistance is increasing as well. And because this and this both increase, flow remains the same. Okay? So blood flow remains constant over a certain range of pressures, especially in the kidney. Okay? And then once you get outside that range, as the pressure goes up, your flow goes up again and you obey Ohm's. Okay? You do what you would expect as the pressure goes up. So the reason what's happening here is you're getting a constriction of this vessel, which means an increase in resistance in response to what is primarily known as the myogenic mechanism. Not much is known about this. If you take an artery, especially from the kidney, and you strip away all the endothelia, you strip away all the nerves, you just have a smooth muscle ring, and you increase the pressure in that ring and you expand the walls, for some reason, nobody really knows, the walls will contract back. Okay? And in fact, you get a net constriction in response to the increase. Okay? So as the pressure in this smooth muscle ring goes up, you would ordinarily think, well, the volume will go up. Well, and the cross-sectional area will go up, and the vessel will actually dilate. Instead, what happens in these arteries is they actually constrict in response. And the resistance to flow goes up. So the pressure in the vessel is going up here, and as it goes up, the resistance to flow goes up to keep flow constant. And again, particularly important in the kidney. Okay? And this is an example of the myogenic mechanism at work. Kind of happens in all the arteries to some extent, not a major factor most of the time. It's really only really important in the kidney. Okay. So we talked about other local factors. That's considered to be a local factor to the nth degree. All it is smooth muscle, nothing else. Metabolic controls are also local factors. These are really important, and once again, they dominate over the central controls. So we can talk about lactic acid. Lactic acid is a vasodilator. And when you see more lactic acid in a tissue, it usually means the metabolism's gone up, and that means that there's a need for oxygen and a need for metabolites, and that means you get a vasodilation in response. Carbon dioxide, when you see more carbon dioxide, that means you probably need more blood flow. You need to get more oxygen into that area. Metabolism's gone up. When you see a drop in pH, hydrogen ions tend to be a byproduct of metabolism. Usually because the carbon dioxide and the lactic acid have gone up, and they make the environment more acidic, meaning you've got a drop in pH, meaning you've got an increase in concentration of hydrogen ions. That can be a vasodilator. We have potassium ions here. If they're increased, a lot of times in active tissue, you'll find more potassium ions outside the cell. Talk about why that will be when we get to the action potential in more detail. That can be a vasodilator. Phosphate and adenosine, these are metabolites, products of ATP breakdown. They are made of vasodilators. Osmolarity can go up and act as skeletal muscle, and that can contribute to a vasodilation. So these are all lumped into what I call one category, local metabolic controls, and they are strong. They're strong, and they usually dominate over the central controls. All right. Basal tone is maintained in these arteries as well. It's maintained by myogenic activity, similar to our autoregulatory response. So basal tone means that there's always some tone in smooth muscle that is maintained even if there's like no neural input or anything like that. Okay, again, it's intrinsic to the tissue. The high oxygen tension in the arterial blood might help maintain a certain degree of constriction. The presence of calcium ions in the plasma getting across that membrane through normal channel activity and through leak might contribute to it. Calcium causes contraction and smooth muscle, just like cardiac muscle, and so that might help maintain some tension in that muscle. And other unknown factors in the plasma. Again, you'd be surprised, basal tone, we've known about that for a long time. You'd be surprised at what's not known about it, okay? Sort of a basic thing. All right, and then finally we have our central controls. We're really talking about the sympathetic nervous system when we talk about central control of arteriolar radius. And that happens through, almost always, through the release of norepinephrine, as in other areas of the sympathetic nervous system. There are exceptions to that rule where you get some acetylcholine released. We call that sympathetic cholinergic activation. We'll talk about that in the autonomic nervous system lesson more than here. But these are released in response to a central detection of a change in mean arterial pressure. Your baroreceptor says, hey, the pressure dropped. It sends pulses to your brain that say, oh, the pressure dropped, I better do something about that. And what the central nervous system does is it increases pulses, neural pulses to these arteries, and you get more release of norepinephrine in particular, and that causes vasoconstriction. When you get vasoconstriction of arterioles, your total peripheral resistance goes up. Remember, this is happening pretty much everywhere, or a whole lot of beds all at once, because your brain is sending out those signals to wherever the nerves go, and the nerves go to a lot of spots. Skeletal muscle, the GI tract, places like that, you're going to get constriction in response. That increases total peripheral resistance. If we increase total peripheral resistance, we increase mean arterial pressure back toward normal. So drop detected at your baroreceptor, that sends signals to your brain that say pressure drop. The brain goes, oh, the pressure drop. It alters sympathetic output through your sympathetic nerves. You get vasoconstriction in various beds around the body. That increases total peripheral resistance. That increases MAP back up toward normal. Okay? This is a reflex response. It's part of the baroreflex response. And this is what your central mechanisms for where you alter arteriolar radius, this is what they do. Okay? This is their purpose. Now, the local factors will override that ordinarily. Under normal conditions, they will. Okay? So you won't cut off blood flow to a skeletal muscle if you're exercising and your muscle's saying, hey, I need that oxygen, okay? The local factors, generally local metabolic factors, dominate over this. But nevertheless, this is important because it's an important part of the baroreflex response, which regulates mean arterial pressure. And remember, your cardiovascular system is tuned to keep mean arterial pressure up, okay? And the reason it's tuned to keep mean arterial pressure up is demonstrated here. So when we look at flow through any of these beds, we're talking about Ohm's law. 90% of life showing up, 90% of the rest is Ohm's law. So the flow through any of these beds is going to be dependent upon that pressure gradient, okay? And if there's a drop in the pressure gradient, then flow is going to decrease everywhere, okay? At the beginning of each of these beds, you're pretty much at the mean arterial pressure, and at the end you're at the venous pressure. If the mean arterial pressure drops, you drop the perfusion of everything. Okay? So your body knows that. It's smart enough to know that. And it's smart enough to know that without maintenance of mean arterial pressure, nothing happens here. And so your body is tuned to keep that mean arterial pressure high at a normal level. The way that you control distribution of blood flow to each of these beds is by changing the resistance to flow in each individual bed. That is done through local metabolic factors ordinarily. Okay? So if I have a skeletal muscle here, like in my leg, and all of a sudden there's an increase in activity and I have more metabolites in the area, I will get vasodilation just here. And I'll get more blood flow just here. I won't necessarily get more blood flow to my brain, which doesn't really need more oxygen if I'm exercising. My skeletal muscle does, okay? So the way that you regulate flow to each individual bed is through the local metabolic factors, okay? All right, that's all I've got. Thank you for your attention, and we'll continue on with this lesson in the next video when you're ready.